Okay, unlike the mean squared error, the log loss is quite complex. To be able to find its derivative with respect to the coefficients, first let's do some advanced mathematics. Suppose that we have the function which is z equals to x cubed y plus 3x squared y cubed. We're being told to find dz with respect to dt, whereas x equals to 4 plus t squared. Meanwhile, y equals to 5t cubed. We are told to find dz dt. Let's draw a tree for this problem. So we know that this z function has x and y as variables. So to draw a tree, we know that z has x on the left side and y on the right side. Okay, not on the right side, just on the one side we have x and y. Okay, but inside this x we have t, and inside y we also have t. To find dz with respect to dt, it's going to be dz by with respect to dt, it's going to be dz with respect to dx multiplied to dx multiplied to dt. So it's going to be dz with respect to dx multiplied to dx with respect to dt, plus the left side of the tree, dz with respect to dy plus dy with respect to dt. This is how we differentiate these complex functions. So now let's start with this part, dz by dx. So z is our main function. dz dx is going to be x cubed y plus 3x squared y cubed. Differentiating with respect to x, so the 3 here will come to the front. Y is a constant, so we just leave it. So it'll be 3x. We reduce 3 by 1, it will become 2. Now we just write this constant plus 2 will come to the front, so it becomes 6x. We subtract this 2 by 1, so it just be 6x. Now what about this y? 3 y is a constant, so we just write it down. dz by dx equals to this formula here. Let's find dx by dt. dx dt. dx, our formula is 4 equals to 4 plus t squared. 4 is a constant, so we'll ignore it. 2 will come to the front, so it becomes 2t. This is dx with respect to dt. Okay, now let's proceed with this part. I'm sorry, this is multiplied to, this is times. So dz by dy will become, where is dz? Z is our main function, so x cubed y plus 3x squared y cubed. With respect to y, this time x is a constant, so it become, we just write it down. If we take the 1, that's the power of 1, will move to the front, this y will cancel out, so it will be just x cubed plus 3x x squared, excuse my writing, this is a constant. What about this y cubed? 3 will come to the front, so multiply to 3 y. If we subtract this by 1, it just remains 2. So our final dz dy will become x cubed plus 9x squared y squared. This is dz dy. Now let's find the final part here, which is this. The final part is dy by dt. Our function for y is 5t cubed. 3 will come to the front, it becomes 15t squared. This is dy dt. Okay, so our final dz with respect to dt will be the first part, which is the first part, this one, 3x squared y plus 6xy cubed multiply to dx dt to t plus dz dy. Where is dz dy? This one, x cubed plus 9x squared y squared multiply to 15t squared. This is our final dz dt. Okay, now back to log loss. Let's see how we are going to differentiate this log loss function. We know that the log loss, the cost function for logistic regression, the log loss equals to minus 1 number of independent and dependent variables. Summation, we start with 1 up to n. So is y the log of, let's say a is our predictions as an activation function. In neural network we would call, let's say a is our p probability plus 1 minus y log of 1 minus a. Okay, a1 ai yi ai yi. Okay, this is our final formula for the log loss. But when we are finding the derivative for each independent variable, we are going to ignore this summation and the n. We are going to add them in the end once we obtain the gradient formula. So our cost function now becomes minus y. Let's also ignore these i's so that it can be easy to write them. Log of a plus 1 minus y log of 1 minus a. Yeah, we don't use this I because we are differentiating at a single point. We have logarithms. We also have y and a as our variables here. To draw a tree, we know that this cost function, just like we did before, has y and a. Inside this a, we know this a is a predictions, and a equals to 1 plus e raised by z, raised by negative z. This a for our predictions in probability terms has z, and this z is a linear model equation, which is beta O plus beta 1 xi. So this z has the items we want to differentiate with, so has beta O. In this case, has beta O, let's say. Now, if we're going to differentiate with respect to beta O, this is the thing we want to find first, the intercept, the y-intercept, okay? Since we are going to differentiate with respect to beta O and beta 1, let us ignore this side. We're just going to go with this root. So we know that differentiating the cost function with respect to beta O which is the intercept. Oh, let's first start with the slope. This is the hardest part. Okay, beta 1. Okay, let's say we start with beta 1, the slope with respect to beta 1 equals to derivative of cost with respect to A multiplied to derivative of Z, which is our sigmoid. Oh man, derivative of A, now it's A, with respect to Z, our sigmoid function, multiplied to the derivative of Z with respect to beta 1, which is the final thing we want to find. Okay, now let's start with the derivative of cost with respect to A. Okay, so to find the derivative of cost, let us go to, because this is our cost function now, let's find the derivative. Let's differentiate this function, so it becomes minus y, on bracket, minus y. We know if differentiating logarithms, natural logs, if you're given log of x, this is equals, if we differentiate this, will become 1 over x. So now this will become multiplied to log of a will become 1 over a plus 1 minus y multiplied to 1 minus a. Pay attention here. This is a composite function, is our outer function, and this one here is inner function. So we differentiate the outer function, then we multiply to the inner function, just like we did on linear regression. Now, once we have already differentiated this outer function, it will become 1 minus a, this is the outer function, multiplied to the inner function, the derivative of the inner function. So the derivative of the inner function, which 1 minus a, derivative of the inner function with respect to a, this one is a constant, so we just remain with negative a. We have the power of 1 will come to the front, so the final would be minus 1. So if we multiply this minus 1 here, this, let us write this down, derivative of cost with respect to a will become minus y a. We introduce this minus on the inside, so minus 1 minus y 1 minus a, negative sign here. This negative, when divided here, will become positive. So our final equation will become 1 minus a. Okay, so this is the derivative of cost with respect to a. Okay, now let us find the derivative of cost of a with respect to z. Derivative of a with respect to z. We go to what is our a. Our a is this function 1 plus e minus z. We know that this is the same as writing 1 plus e z. We introduce minus 1 power, the inverse in the other words. This is the same as writing this. So we start differentiating this. Minus 1 will come to the front. It becomes minus 1 plus e minus z. Now, if we subtract this negative 1 by 1, it will become negative 2. keep in mind that this is a composite function. So that means what we did here is for the outer function. This the outer function. Now what's about the inner function here? Now let's go to the inner function, which is 1 plus e minus z. Okay, 1 is a constant, we will ignore it. We just remain with e minus z. To differentiate this power, we come to another thing, differentiating powers. I will have the video for calculus linked below, because this can become complex for someone who skipped the mathematical classes. Okay, so differentiating the powers, e over x is the same as ex multiplied to the derivative of x, the power. So this is the same as, so this minus z is the same as e minus z multiplied to the derivative with respect to z. So now if we find the derivative with respect to z, z has the power of 1. 1 will come to the front, so it will become minus 1. The z will cancel out, so this final output will be minus 1. So here we'll minus 1. We'll multiply to minus 1. If we do the multiplication here, the final output minus 1 become positive, so it will be e negative z raised by negative z, the form 1 plus e raised by negative z minus 2. This is the same as writing e minus negative z divided 2 1 plus e minus z square, the inverse of what we did here. Correct? Now we know that a equals to 1 over 1 plus e raised by negative z. So that means a square equals to 1 plus e minus z square. So this can be also written as e minus z multiplied to a square. So that means but we know that on the denominator here we have e raised by negative z. To find this e, we can also extract it from this equation. So 1a equals to 1 plus e raised by negative z. Let's find this e raised by negative z. So we'll do the cross multiplication here. So it becomes a 1 plus e minus z equals to, in bracket, equals to 1. So it becomes a plus a e minus z equals to 1. Okay, if we take this 8 to the other side, it becomes minus a. We have a e minus z equals to 1 minus a. Divide by a, divide by a. This will become 1 minus a divided by a. This is the value for e raised by z. If we subtract this to this formula here, this formula we have here, e minus z multiplied to a square. This is the value of e, so 1 minus a divided by a multiplied to a square. This a will cancel with this value of a1 here. So the final dA dz, that's what we was finding here. The a dz become 1 minus a multiplied to a. This is our final dA dz. Now we only have remain with one part here, which is dz with respect to beta 1, the final part. dz with respect to beta 1. Now the formula for z is beta O plus beta 1x. Okay, this is simple. To find the derivative with respect to beta 1, this x is a this beta O is a constant, so we just remain with beta 1x. Now this x becomes a constant too, but we know we have the power of 1. If we take 1 to the front, we just remain with 1x. This is equivalent to x. So dz with respect to beta 1 equals to x. Now let's sum this up. Derivative of to beta 1 equals to, we have dz, the derivative of cost with respect to a minus y plus 1 minus y, 1 minus a divided by a, multiply 2 1 minus a. This is a, not to be confused, excuse my writing, multiply 2, the final part, x, multiply to x. Okay, so let's simplify this part. Find the denominator will become a, 1 minus a, 1 minus a, so it become minus y inside 1 minus a plus a 1 minus y. If we simplify this, it will become minus y minus a plus ay plus a minus ay, a minus 1 minus a. That's a bunch of papers. This finally becomes, this and this will cancel out, so it become a minus y, a 1 minus a. Okay, multiply to 1 minus a, correct, multiply to x. We know that this and this will cancel out, so we just remain with a minus y, x. So this is our final derivative of cost with respect to beta 1. As complex the function was, it comes down to this simple function. So to find the derivative of cost with respect to beta O, if we go and multiply this 1 instead of x, which was the cost, the beta 1, we'll have this value of x will be cancelled out. So the derivative of cost with respect to beta O equals to a minus y. Meanwhile, the derivative of cost with respect to beta 1 equals to a minus y multiplied to x. This function looks similar to the one we had on linear regression, but this is the theory on how we were able to obtain gradient for the log loss function with respect to beta 1 and beta O. That's it.